So here we have an acyl Coa synthetase, and it's an enzyme that's going to be important for the triacylglycerol resynthesis. So after two fatty acids and a monoacylglycerol have made their way into your duodenal mucosa, they're going to run into an enzyme like this one that's going to put them back together into a triglyceride. Now this whole thing is not completely active. The active site is actually hidden right in here. You can see that a little bit better if we make this a mesh. So we can show this as a mesh, so you get a sense of the surface. And a couple things are bonded to this already. One is coenzyme A, which is going to be crucial for us, and the other is adenosine monophosphate, which you'll see as a part of this mechanism. So I'm going to make these represent those in this licorice way, and you can see how that is fitting into that little pocket there. You can see it clearly here, and as you move around it's covered by the mesh, so you can sort of get a sense for what that enzyme pocket looks like. You can see how it reaches into the enzyme and it opens up to the outside world right here. So we can show those as spheres again. So if we just wanted to see the active site, we can click on this coenzyme A and this AMP. We can select around them, so we'll modify these. And expand, let's say by 5 angstroms. We'll hide everything else that's not selected. And so this is that region. Now let's show this a little bit differently. We'll show this as the licorice, and we can zoom in on that also and get a sense of what these look like. Now if we just want to see the coenzyme A and the AMP, we can make those stand out a little bit by showing those as spheres. You can sort of see how they're fitting into that active site around them, those groups. Now this right here is coenzyme A, and then this smaller group here, that's adenosine monophosphate, fitting into the active site of our enzyme. So one more time, our enzyme is right here, and this is an acyl Coa synthetase that's going to be turning helping to turn two fatty acids and one monoacylglycerol back into a triglyceride before it's transported to the rest of your body. Here we have coenzyme A. It's going to be important in activating our fatty acids so that they'll be more reactive. Ultimately, this is going to, usually in organic chemistry, when you turn you want to make a carboxylic acid more reactive, you would turn it into something like an acid chloride. But in biochemistry, instead of putting a chlorine leaving group, really good leaving group, where the OH was, you'll often have some sort of a sulfur. And that's the role that this coenzyme A is going to be playing. It has a sulfur on this one end of it, and that sulfur is going to make a good leaving group on what was a carboxylic acid. Here this is a ball and stick model, but you can also visualize this in the van der Waals frames, and you can see that there. Another fun way to visualize these molecules, so this is the coenzyme A. Another fun way to visualize them is to see the dipoles on them. And so here you can get a sense of where the positive and negative charges are on the molecule. And these are approximations, but on the whole, wherever you have blue, that's where there's some positive charge on the molecule, red is negative, and green is neutral. So as you can see that there's a lot of polarity in this. This is going to be a really water-soluble compound. Here we have ATP. ATP is going to be important for the resynthesis of these triglycerides once they get into your duodenal mucosa. And here you have the adenine part, the adenosine part, and the 3 phosphates. So notice each of these orange spheres is a phosphorus atom, and so you have the 3 phosphates here. So this is the ball and stick model of ATP. You could also visualize this with the van der Waals spheres. that are loading. And you would get something that looked like this. So you can see that ATP molecule moving around. You can see the 3 phosphates there, and then the blue adenine ring